Welcome to my PhD thesis defense. I will discuss my thesis on computer methods for collision processing, from sound to topology. Physics simulations are used to simulate the real world in many application areas, including animation, augmented reality, digital fabrication, and sound synthesis. In each of these scenarios, objects must interact with each other, oftentimes through contact. Here is an example of layers of chainmail stacking on top of each other, a shopping cart rolling away, and a scarf falling onto an incline. In many animation and AR applications, sound effects can improve realism and the feeling of immersion. Many of these effects occur when objects are in contact, such as during a footstep or a croquet shot. To synthesize this, we can use Foley, where an artist records impact sounds to match the picture, or procedural audio, where sound is synthesized according to programmatic rules, or physics simulations. Among the three techniques for sound synthesis, my work focuses on improving physics simulations. Here's an overview of how this works. When objects collide, their surfaces vibrate. These vibrations drive pressure waves through the air, which travel to our ears as sound. Many prior works model the vibration of objects in impacts either with each other or the ground. However, the ground vibration sound is missing in many of them, and my work addresses this issue by modeling the ground vibration. On the other hand, contact events keep objects from passing through one another. For example, in this picture, even though gravity is pulling the cups down, they still sit on top of each other and they don't pass through each other or fall through the tray because they're in contact with each other and the tray. And so in the physics simulation, the simulation must detect these contact events to prevent interpenetration, and this can also be costly. So in garments made of yarn, yarn can also pull through each other in the simulation if collisions are not detected. These topology changes can be noticeable. For example, look at the chevron pattern on the right. If two yarns were moved out of place, then the pattern can unravel and look very different. So my work develops a certificate to verify that this topology remains the same. So one thing we can use is that linking numbers are a topological invariant. A linking number between two oriented closed curves is an integer that measures how many times one curve winds around the other, like in these four pictures. If curves are unlinked, their linking number is 0. It is invariant to deformations where the curves don't pass each other. So a key insight in my work is that this invariant can be computed to verify curve topology. And so my thesis makes claims on two specific subproblems in collision processing. First, an idealized, temporally regularized closed-form solution to Lamb's problem can be used to cheaply synthesize ground impact sounds with physical realism where it was previously missing. And my second claim is that the computation of linking number certificates aided by acceleration structures can be used to efficiently and reliably verify the topology of Loopy models, such as yarn level cloth garments, stitch patterns, chainmail, and double helices when they undergo deformation. And so here's an overview of the rest of this talk. The first half of my thesis covers sound synthesis research that was contained in my DAFX 2019 paper on the impact of ground sound and my SIGGRAPH 2018 paper on wave-based sound synthesis for computer animation. The second half covers topology verification research from my SIGGRAPH 2021 paper on fast linking numbers for topology verification of loopy structures. So I will now discuss the sound synthesis of ground sound. let's explore the problem of physics-based sound synthesis for computer animated effects. In 2018, we built a wave solver to synthesize sounds for various animated phenomena. The goal was to provide an audio analog of global illumination, which is a powerful tool for visual graphics. We simulated the sound from many physical interactions, including hitting a cymbal, shaking a metal sheet, dropping Lego blocks, and dropping a spooling bowl on the ground. So our wave solver used a spatial finite-difference time domain grid to discretize the air medium. And so in this grid, what we do is we discretize the air into cells in space, and our finite difference solver time steps this acoustic wave equation to propagate the sound waves. Sound sources are actually incorporated by using their accelerations along the boundaries as boundary condition. So similar to programmable shaders in graphics specialized for optical phenomena, we developed a shader abstraction so that sound phenomena can be implemented as a shader. In this interface, the shader simply provides a function that evaluates the object's acceleration, an. When the solver needs this value, it calls it at a specific position and time, including on the object and on the ground. This abstraction lets the solver evaluate many sound phenomena using the same interface. We added a shader for rigid body modal sound, acceleration noise, fluid sound, thin shell sound, and more. Here's an example using rigid body shaders. To give a background on these shaders, they use a reduced order modal decomposition following a linear finite element model to determine the elastic vibration modes. Then anytime we have an impulse, say against the ground, it's projected into modal space, and then vibrations are expressed as surface accelerations. Object-only models in prior work typically ignore the wave interaction between objects. So here is a bowl sound rendered without and with floor scattering. That was without floor scattering. And this has the floor scattering. The spinning bowl and the floor create a complex system that has cavity resonance that changes in time. And we capture these results, as you can see in this spectrogram, where the frequency lowers over time. The object-ground wave interaction is also a key to modeling the sounds of Legos landing face down or up. Here's a spooling bowl on the ground again. And just to clarify, spooling stands for spinning and rolling. We only simulated the sound emitted by the bowl in this interaction and used the ground as a passive scatterer. The same can be said for the Lego examples. So the question is, what can we do to model the ground sound? In these examples, the sound came only from the object and not the ground itself. During an object-ground collision, there are actually three types of sound emitted: ringing modal sound from the object, transient acceleration noise from the object, and transient ground emission. So how do we model this last sound? And when is it important to include it? This is a question we will try to answer. Some past papers like Zheng and James 2010 actually modeled the ground using a large slab. We will develop a transient ground sound model for infinite grounds. So to model the ground sound, we must first model the vibrations in the ground. The geophysics community has existing work on this. In particular, here's Lamb's problem, which is well studied. If we have a force F of t applied at a point on the ground, then at location r and time t, the problem asks us to find the vertical normal displacement of the ground, u of rt. And this can help us model ground sound. Fortunately, in 1955, Picaris found a closed form solution to this problem. in the right, it's actually in the blue line. This is a plot of the surface displacement with respect to time at a fixed location. Unfortunately, there are 4 singularities. Their names aren't that important, but if you're curious, the first arrives at the arrival of the P wave, and the second at the S wave, and the third at the R wave. These singularities can make it numerically difficult to evaluate. So how do we find a simple solution that does not have the singularities? In graphics, Deggos and James dealt with singular elastic solutions by regularizing it with smooth delta functions. Similarly, we can use the fact that impulses aren't instantaneous and regularize the Picard solution by convolving it with a smooth delta approximation of the impulse force profile. We use the 4th order function f, illustrated in this figure on the bottom. These are f's with different timescales. And this can be used to approximate the force profile. The corresponding smooth Picard responses are plotted in the non-blue lines on the right. Each of these uses a different impulse timescale. As you can see, there are no more sharp singularities. Here's a visualization of a regularized Picard's impulse response. We use an initial impulse that came up out of the floor, as you can see, and the color map corresponds to the height. Red is higher, blue is lower. Here are the approximate locations of the P, S, and R waves, which are now smooth. So our function f has a simple closed form convolution with the Picard solution, u sub n, and it eliminates the problematic singularities. This allows us to easily evaluate the surface acceleration after each impulse. Basically, after we have an impact, we set the magnitude and from the impulse and the epsilon from the Hertz contact timescale of this impulse. And we can evaluate the convolved expression f convolved with u. And in fact, we have the closed form expression for the displacement. And so we hope this result is useful to the community. This expression fits on this slide, and it can be evaluated directly at any position r and time t just by plugging it in. And that gets us the vertical displacement. We can use, say, Mathematica to take time derivatives to get the surface acceleration. So now that we have the surface acceleration, there are actually 2 ways to synthesize the sound. The first method is to use the Rayleigh integral, which directly synthesizes sound from an infinite plane. This method does not account for occlusion or scattering between the ball and the ground. When the listener is overhead, this integral can be simplified into a 1D integral and evaluated very quickly for most scenarios. If it's not overhead, it's a 2D integral that can still be evaluated in a reasonable amount of time. The second method is to use the finite difference time domain wave solver that I showed earlier, and we can incorporate our ground sound model as an acoustic shader. This allows us to enrich those examples of ground sound. We simply would evaluate the acceleration at x and t and supply it to the wave solver. So here's one scenario where we drop a ball from a fixed height onto a floor. Here are the results. So on the left is an example with the ideal steel ball and a wooden floor generated from the Rayleigh integral. We use the same impulse force profile on the ball as on the floor and an overhead listening point. The orange line is the ball sound. The green line is a combined sound, and the blue line is a floor sound. What I want you to see here is just that the combined sound actually has a different shape. This is pressure with respect to time than just a ball sound by itself, which means that adding the floor sound made a difference here. This all occurs in a fraction of a millisecond. On the right is a similar scenario with a steel ball and concrete ground, which we use the finite difference time domain wave solver and stepped at 44 kilohertz. The extra echoes after the main sound mainly come from the waves reflecting between the ball and the ground, which is something we don't capture in the ideal model. I will show a few audio results. Next. So here are some example sounds from the wave solver. We drop a large spherical granite rock onto a soil ground. In the visualization, the sphere represents a granite ball and the tiled floor represents the soil. The sounds are a little bit soft, so listen carefully. Here's a rock sound. Here is a ground sound. And here's a combined sound. In this scenario, most of the sound comes from the ground. We now drop steel ball bearings onto a wooden floor. Here's a ball sound. Here's a floor sound. And here's a combined sound. In this scenario, the combined sound is a little bit different from the ball sound by itself. Now let's drop plastic dice onto a wax floor. Here's a dice sound. Here's a floor sound. And here's a combined sound. In this scenario, the floor sound is very soft and most of the sound comes from the dice. As you could tell, it depends on the scenario which sound is more dominant. And so here's some analysis on how the different parameters affect what you hear. Two parameters are ball density and ground stiffness. From our analysis, the ground sound is louder when you have higher ball density or lower ground stiffness. The ball sound is actually unaffected by these parameters. Another relevant parameter is the listening angle. Notice that sound is louder when the listener is overhead. So in this plot, the angle is on the x-axis and the sound intensity is on the y-axis. When we get to a lower listening angle closer to the ground, the sound drops in intensity. However, the ball sound drops more drastically than the floor sound. And this is about a 10 to 20 decibel difference at 5 degrees. The dipole is an approximation for when the ground gives no reflection, and the quadrupole is when the ground gives a full reflection. So we tested ideal ball ground impact scenarios for 8 different materials. And the top table shows what happens when the listening point is overhead. This is green, means the ground is louder than the ball. Orange or beige means the ground is softer but still audible. And white means the ground is too soft to be heard. The bottom table, however, is when the listening point is much closer to the ground. The materials are arranged so that those with lower ground stiffness are on the right, and those with higher ball density is on top. You can see that ground sound matters more when with lower ground stiffness, denser balls, and lower listening point angle. So in summary, we developed an idealized model to synthesize physics-based ground sound as an acoustic shader where it was previously missing. As you can see, it depends on the specific scenario, whether the ground sound is audible versus masked, such as object density, ground stiffness, and listening angle. There are, however, a few limitations that inspire future work. Our model is based on an infinite linearly elastic half space. Real-world scenarios can be quite different from this. The future work can perform experimental validation. For example, they can validate against the real world. Future work can also model resonant modes of buildings, such as floors with finite depth and walls of a finite thickness. Lastly, we've only done normal forces. We can also model the the response to tangential forces caused by contact friction. Now let's switch gears and discuss fast linking numbers for topology verification of loopy structures. Let's take a look at this chainmail piling simulation from the Chrono simulator. At a fixed accuracy, collisions can be missed between rings. If we pay attention to the region in red, a loop in this chrono simulation falls off and rolls away. Now, this simulator is actually also used to pack chainmail into a box for 3D printing. And topology issues, look, right now it's falling away, just like that. Topology issues can result in incorrect physical results. So it can be impractical to have a human in the loop to continually watch and retry these simulations for topology violations. Here's another issue. In a yarn level cloth simulation, there can be hundreds of thousands of thin spline segments, like in this sheep sweater on the left. A pull-through occurs in a simulation when yarn illegally passes through each other. For example, let's say the green yarn is on top of the blue yarn at first, like in the middle top picture. A pull-through could cause the blue yarn to pass through the green yarn, ending up on top because it misses a collision. This is why yarn simulations must take tiny time steps. So a motivating question is, for a complex yarn model, can we take larger steps and verify the topology after stepping? And so thin loopy structures are everywhere. For example, in yarn level cloth models, rubber bands, chainmail, and DNA ribbons. Many operations, such as simulation, reparametrization, compression, and yarn relaxation, can all violate curve topology if not done carefully. Because these models are so detailed, it can be very hard to visually detect any violations. So in this work, our goal is to automatically verify the topology of these loopy structures as they undergo processing. What we propose to do is, given the model state, compute a topology checksum. This can be done before, during, or after processing operations to validate topology. We also handle inputs with a generic number of curves, segments per curve, or curve segment type, such as splines. Our method verifies topological structure during processing operations and can detect any violations for us. In these examples, we compute a checksum during various stages of a simulation and detect changes in the topology. On the left, as the rubber bands slide in the simulation, we highlight in red the rubber bands that illegally link with other rubber bands. And on the right, we highlight rows of a yarn level cloth model that pull through each other during a simulation. As we discussed earlier, one insight we can use is that linking numbers are a topological invariant. It does not change under deformation unless curves pull through each other. We can use a matrix of pairwise linking numbers as a topology certificate. There are many ways to compute the linking number, and we explore two of them in this work. First, we can find a regular projection onto a 2D plane, and then for every crossing, count based on the relative orientation, such as here and here, of the two curves. The second way is to compute the Gauss linking integral. And to give you an intuition of where this comes from, it has a physics analogy. So suppose the blue loop is a circuit with a fixed current I, and the red loop is a test loop. We want to find the current enclosed by the red loop. And so we can use the Biot-Savart law and Ampere's law. We can first apply the Biot-Savart law on the blue loop to figure out the B field at a point on the red loop. And then once we have the B field, we can apply Ampere's law over this entire red loop to integrate it. And that current enclosed is equivalent to the linking number, since it measures how many times the blue loop passes through this area. So many works in the past address geometric verification for inside-outside tests. For example, if we have two polyhedra, vertex face and edge-edge tests will tell us whether they interpenetrate. In this case, a vertex face test will detect an interpenetration between these two objects here. And now an edge-edge test is better suited for detecting interpenetration. And this is why both tests are used. And these tests are discrete because they verify individual states have no interpenetration. Another class of methods, continuous collision detection, verifies that an entire trajectory is collision-free. There are trade-offs between discrete and continuous tests. And to clarify, our method is a discrete test in that it is a topology check on individual states of an animation. Generalized winding numbers, generalized inside-outside tests to curved surfaces. That's another set of works. So in a way, linking numbers with generalized edge-edge tests to closed curves. This is because the numerator of this integrand is actually the edge-edge determinant between the differential vectors dr1 and dr2 along the curves. And most prior works use a brute force quadratic algorithm, whether it be counting crossings or the Gaussian integral. As far as we're aware, no existing work has scaled linking number computation to generic large input. And so our method uses 3 stages to carefully and efficiently compute the linking matrix. Given an input set of loops, we first perform a potential link search to get a list of potentially linked pairs of loops. Then we discretize curves into polylines. And finally, we process the polylines to compute a sparse triangular linking matrix. The rows and columns of this matrix correspond to curve numbers, and the entries are the linking numbers. This is the final topology checksum. 2 structures with the same linking topology would have the same matrix. So stage 1 is the potential link search. We first compute bounding boxes and build a bounding volume hierarchy, which is a BVH. Because 2 loops whose bounding boxes don't intersect would have no linkage, we can just output a list of pairs of intersecting bounding boxes as a list of potential links. This allows us to code the list of potential pairs greatly. For example, in the chainmail example, if R is the number of rings, then the number of potential pairs goes down from order R squared to R. The second stage is discretization to convert the curves into polylines. We start with the segmented curve and compute 3D bounding boxes around each segment. At this stage, we detect any zero-length segments so that the user knows to throw them out because they can cause problems in computing the linking number. For any boxes that overlap with those of other curves, we simply subdivide their segments into 2, and then we repeat this procedure until no more boxes overlap. This procedure terminates quickly if the curves do not intersect. And if the boxes shrink to machine epsilon in size, then we simply return with the error because that indicates that the curves are intersecting. After we finish this subdivision, we deform each curve segment into a line segment. Line segments are more convenient for the linking number computations in the next step. So stage 3 is the actual computation of linking numbers. The input is a list of potentially linked loops, and the output is the linking matrix. There are many methods that we explored for this stage, each with their own advantages. The first is counting crossings, and the other methods use the linking integral. In the interest of time, we'll only discuss counting crossings, direct summation, and Barnes-Hut integration. To count crossings, we have to project line segments onto a 2D plane. So we need a regular projection. Basically, if no 2 vertices or intersections coincide at the same point, then the projection is regular. So we first generate a randomized direction, and then we use the sorted directions of line segments to rotate it to avoid degeneracies. If the loops have a lot of points, we build a 2D BVH of segments from one curve. We then iterate the other curves in parallel and use the BVH to detect intersections between the curves. At every intersection, we increment or decrement the linking number based on the sign of the crossing. The advantage is that this is a very simple and fast order n log n and parallel algorithm. However, one disadvantage is that the quality of the projection can be a concern in case degeneracies occur. So if this is a concern, we also explored methods that use the Gauss linking integral. So the second approach is doing an Embody direct summation of the thinking integral. We can rewrite this integral as a double sum of integrals over line segment pairs. We call each line segment pair value lambda ji. And this would correspond to the integrand evaluated over a single pair of segments, in this case between the red and blue segments. Lambda ji has a closed form expression from the sine solid angle formula, which involves evaluating two arctangents. It is well defined when the curves do not intersect. So we evaluate this double summation in parallel on the CPU and GPU. The advantage is that the parallelization scales really well and is very fast for small loops. However, it's an order n squared algorithm, so it can be very slow for large loops. Another method is Barnes-Hut. Barnes-Hut is a popular n log n method for evaluating Embody problems. We pre-build a BVH tree of segments for each loop and pre-compute their multipole moments. Here I illustrated two nodes for the beige loop. So all of these are segments within the beige loop, and these are bounding boxes of them. During evaluation time, we traverse both trees and evaluate nodes in one loop. So here's the blue loop, which has nodes, against the other loop. The Barnes-Hut beta parameter, which is used in the threshold, determines how to decide if nodes are in the near field or far field, based on how far apart they are compared to their size. So for nodes in the far field, such as this pair, we just use a far field multipole expansion to estimate their contribution. When they're in the near field, we traverse their children until they're in the far field or they are leaf nodes. For leaf nodes, we use a direct expression from earlier for a pair of line segments. We also compute an error estimate while traversing this tree and increase beta if the error is too large. The advantage of Barnes-Hut is that it's fast with a lower overhead than the other fast methods. But like with counting crossings, it's slow when the loops have long segments in them. And so here are some example results. In this example, we pack a Kusari chainmail shirt of curved rings into a box for 3D printing. It has rigid curved rings, which we simulate with Bullet in Houdini. The simulation takes 15 minutes to complete. We will first use large time steps, which can miss collisions, and then show smaller time steps sizes. Here's a simulation with large steps. The left video shows the simulation. When violations are detected, the corresponding rings are marked in red in the right video. This one has lots of violations, as you can see. With medium steps, a few links are still broken. With small steps, we verify that the topology is maintained. We can also verify yarn models that are expressed as stitch meshes. In the stitch mesh paper from 2012, they mentioned two ways they could have connected stitches. For example, here, the stitches are arranged in a helix. This is a knittable geometry. It's one long yarn. So my method cannot verify this because it requires many closed loops. However, most stitch mesh models actually use the structure on the right, which arranges stitches in the cylinder because that's easier to simulate and relax. In this structure, every row is a closed curve. And so my method can verify the topology of these yarn models. So first, we can analyze the topology of this input yarn model. We downloaded this relaxed model from the stitch meshes paper. And knitted structures like this should not be linked between any loops. And the relaxation process attempts to maintain that. In the paper, the sweater took 7 hours to relax. My method was able to verify in under a second and detect these linkages marked in red in the model. Zooming in, we find, for example, that this small green loops only has 3 curves coming through it, when in the figure in the paper, it should have 4. So this indicates that a pull-through occurred during the relaxation process, and it should have been reran with a smaller time step size. Now here's a yarn level class simulation, where we take a sweater and drop it onto the ground. I will first show a simulation with large time steps, which has topology issues, and then change it to use small steps. Here's a sweater sim with large implicit steps at 2400 Hertz. Topology violations are marked in red. Now here's a simulation with smaller steps at 6000 Hertz. Both simulations took many hours to complete, but only a fraction of a second to verify each visual frame. Here's another stress test simulation where we twist a knitted tube. Even though it's not apparent, a pull-through has actually already occurred at this point. Let's rewind a bit and see what our method says. Even though it looks like it destabilized very quickly, because there are small time steps, our method actually detected a violation over 1,000 steps before the destabilization. I'll replay this one more time. Now let's drop 1,000 separated rubber bands onto an inclined plane. On the left, we use 4 substeps per frame, and violations are highlighted in red. On the right, we use 20 substeps per frame, and our method verifies that it is valid. It can also be appealing to use cheaper deformers and yarn level simulators. In this example, we started with a vellum simulation of a glove as a deformable TET mesh. We animated our glove yarn model as an embedded deformation. And our method verifies that the topology remains valid. Here's the final render. Our examples so far required our models to have only closed curves. However, if an open curve structure is a type of braid, we can also verify them by virtually closing the loops. A braid consists of 2 rigid bars with curves attached between them. In this example, we set up a chevron stitch pattern as a braid and verify its relaxation. We attach this chevron stitch pattern to 2 rigid bars, making it a braid, and we relax it while slowly pulling the bars apart. This relaxation uses small steps, and we verified that it is good. When we retried with larger steps, our method detects a pull-through very early. Notice the difference from the good relaxation. In the next 2 examples, we verified 2 geometric processing operations. In both cases, we start with yarn models with Catmull-Rom splines. In reparameterization, we gradually decrease the number of control points by resampling points along the Catmull-Rom curves. In compression, we maintain the same number of points, but reduce the precision of each coordinate gradually down to 10 bits of precision. All our verifications take less than a second. Here are the reparameterization results. So that was the reparameterization results. And here are the floating point compression results. And so you can see that our method can basically validate topology for various settings for reparameterization and compression. So we analyzed our runtime performance. In most cases, stage 3, the linking matrix computation, takes most of the runtime. The counting crossings and Barnes-Hut methods are the fastest in most cases, taking advantage of tree structures but still remaining cheap. In particular, the GPU Barnes-Hut algorithm shines on large double helix ribbons, taking only 5 seconds on a 20 million segment ribbon. This could be useful for DNA topology computation. Counting crossings and Barnes-Hut are also efficient in examples with more loops, such as the deformed glove. Here's a plot of the runtimes for the CPU methods. The green axes are the counting crossings runs, and they're the fastest in most cases. The blue diamonds are Barnes-Hut CPU runs, and it is the second fastest in most cases. As you can see here, most of these have the X and the diamond on the bottom. Both methods finish all these examples in under about a second. The GPU runtimes are actually in the same ballpark as the Barnes-Hut and CC for most examples shown, and that's because these loops are still relatively small. So it's almost the same runtime. We explored practical algorithms to efficiently monitor Loopy structured topology. This has many applications in graphics, such as with yarn level cloth, chainmail processing, animations, and simulations. We found that either counting crossings or Barnes-Hut is competitively fast for most applications. One limitation is that linking numbers are only a sanity check. It's possible for multiple quick pull-throughs, for example, to end up with the same linking numbers. The other limitation is that we still cannot verify generic open curves. This leads to our recommendations for future work, which include simulation rollbacks, verifying curves with finite cross sections, as well as expanding our checks to generic curves. So as a summary, in sound synthesis, I derived a closed form idealized model to synthesize ground sound where it is missing. I found that ground sound is especially relevant with a low listening point angle, dense objects, and soft grounds. Future work can incorporate damping, contact friction, finite depth floors to increase realism. With topology verification, I use acceleration structures to efficiently compute the linking matrix certificate in order to verify the topology of loopy structures. This allows them to be robustly processed. Future work can expand this to knittable yarn models, periodic yarn patterns, and hair. Thank you everyone for coming to my thesis talk. In particular, many people have helped make this thesis possible. I would first like to thank my advisor, Doug James, for giving me thoughtful guidance all these years. I wouldn't have gotten this far without him. I also thank Julia Smith, Pat Hanrahan, Leo Guibas, and Gordon Wechstein for serving on my committee. I also thank my collaborators in our research group, as well as other collaborators during my PhD. I also thank the National Science Foundation for their fellowship program, which funded most of my PhD, as well as many other entities that have donated to my research. I also thank my lab mates in Doug James's group, as well as the rest of the Stanford Graphics and other groups, and our group admins for providing a supportive work environment these years. I thank my family greatly for their love and encouragement and support all these years as I pursued my PhD. I'm also grateful that during the COVID-19 pandemic, I was able to spend so much time with my parents, Jifa and Jian, my brother, Alan, and our dog, Cooper. I also thank my friends who supported and encouraged me all these years in the various cities that I lived in during the PhD and the pandemic. I had trouble fitting you all on this slide, so here's my attempt, and there are countless others as well. Thank you.
Needs to be some applause.
Okay, fantastic. Thank you. Okay, so we have time for questions from the public audience. So anybody does anybody have any questions or comments?
Could we just speak up?
Yeah, please unmute yourself.
Great talk, Ante.
Thanks.
I was curious, it seems like using linking number as the invariant for knit structures in particular, it seems like it's useful, but also that knit structures have a sort of Borromean ring sort of quality to them, where the natural arrangement is everything appears as if it isn't linked, although that obviously isn't the case. I was wondering if you thought about that at all, whether there was any other invariants you considered for dealing with this.
So I have thought about it. I ended up choosing linking numbers. So I guess to give some more context, if you have rows that are closed loops and your structure is all knits and purls or various knit stitches, then you end up with a linking matrix of 0 everywhere if everything is correct. And so that's what Gilbert is asking about. And I think basically I chose linking numbers sort of because they're easy to compute on a large scale. And the sort of problems we want to detect are where you have one pull through at a time. And so in this case, if you just have one pull through, you're guaranteed to change a linking number. And so the hope is we can check it frequently enough and our simulation is done sort of carefully enough that most of the time it'll just be one or a small set of pull throughs. And I've seen most of the time when we have issues with multiple pull throughs, it ends up still changing the linking number. Like it's just as likely for 2 pull throughs to bring it back to 0 as to bring it to some other number. If you have like say 13 pull throughs and it can't get back either.
I have a question, if that's okay.
Sure.
Hi, Ante. That was great. I have many questions because there is a lot of really cool stuff. But okay, I'm gonna stick to one. And I guess my question on the topology verification that you showed, is there in your method in particular, right? Is there is the correctness of the method guaranteed in terms of like, could you have false positives, for instance?
So from what we've seen, at least the way I've used it, if it tells you that there's a violation, then you can't. There is a violation. So it can be incorrect in that it misses a set of violations, but it cannot. When it tells you the linking numbers are different, then they are different. And this is something. And so this also depends on which computation method you use as well. So the Barnes-Hut, for example, gives you an approximation. And so that's what I attempted to do with the error estimate as well, which is when the error is detected to be too high, like say larger than an integer, if you have a structure with say a linking number of 1 billion or so, then it would retry with a more aggressive accuracy tolerance. However, counting crossings has always been accurate to the right integer.
There's a few more questions on the chat. Feel free to unmute yourself and just go ahead and ask them directly.
Oh yeah, I'll take a look. So how long does it take to render the sound compared to rendering the videos? So I think that also depends on how accurate you want how good you want the video rendering to be and how accurate you want the sound to be. I actually, these methods, I would sort of say they're, so the ground sound is more designed for the finite difference time domain. solver, and that's meant to be a slow but accurate solver that sort of shows you what's possible. So on some of our best machines, it takes about 30 minutes to generate a second of sound. However, using the Rayleigh integral, you can generate sound in, say, a few seconds if it's overhead, or if it's not overhead, it could take about an hour or so.
Wow.
What's the cause of that like giant delta between the overhead and like other sound?
Oh, so let me go back to that slide very quickly. I can't find this. I sort of hit this in showing this, but the Rayleigh integral is a 2D integral. And I should say I didn't use I didn't optimize for how to evaluate this efficiently. But this is a 2D integral, and so that's why it's so much more expensive to evaluate both. But when it's overhead, there's enough symmetry that you can collapse it down to a 1D integral.
Yeah, that makes sense.
Hi, Ante. Great
Oh,
talk.
hi. Thanks for coming.
Yeah, of course. I had a question about the his linking numbers thing. Is there like a version of that that would work for cylindrical shells? Do you think?
Could you clarify a bit?
So let's say you have two loops, two like closed circles, and they're linked, but now give them each a little thickness, which I mean, in my mind is actually going to be like a time dimension. There's some sort of invariant there you could conceive of that would.
Yeah, so I think that could be a good next step to this work. So I guess a simple way you can do is just put a ring, put an underlying curve inside the shell. But another thing you could do is do what I did with my sound work and regularize, like smear the linking number over a region. So smear this integral over a region. And then so when you see two cylindrical shells pulling through each other, it would be something that's a continuous change in the value between two integers. So that's one possibility, but we haven't really explored much of this.
I see. Oh, cool. Thanks for the insights.
Hi, Ante. I was interested in the point you made about using your checksum to kind of like refine simulations when they're using too coarse of a time step. Could you say a bit more on how much you would look into rewinding and how you might like first steps at such an algorithm?
Sure. So one big thing to notice here is that the violation mainly happens during a small time region. Like during the simulation, when it was falling, it was fine. And after it's on the ground, no more new violations happen. Most of these violations happened the moment it hit the ground. So one thing you could do in a simulation is normally take some aggressive time steps or have some sort of inaccurate settings. But once a violation is detected, you roll it back to the last valid state. And then you try to step it again with smaller steps. And so that's what I was envisioning, but we haven't done any of this yet.
Cool, thanks.
Okay, if there are no further questions, then I would say let's close the public session and reconvene in just maybe 2 minutes or so in the private session with the committee.